In this video, we will solve the first two parts of an exam task on mass transport given in January 2023 in the course Mass Transfer in Environmental Engineering. The first two parts of the task are as follows. A test tube with acetone is placed in a fume hood, that is under good ventilation, at a constant temperature of 20 degrees centigrade. The test tube, a perfect cylinder, has an inner diameter of 2 cm, is 5 cm high and half filled with acetone. A. What is the evaporation rate currently? B. Make a schematic drawing of how the evaporation rate will change over time and explain why. There is also an unrelated theory question C that we cover in another video. In the context of this course, I consider this exam task a rather simple and straightforward task. We have the same setup as in compulsory task 2, so it should come as no surprise that this is Stefan diffusion, that is, diffusion through stagnant component. Why? Well, as the acetone liquid evaporates, the liquid volume needs to be replaced by a gas volume. But the gas volume contains way less molecules than the liquid volume, and thus we can neglect the transport of air into the column. So the terms in Stefan's equation for mass transport, that is, the evaporation, can be expressed as the diffusivity divided by the film thickness, so 5 cm divided by 2 equals 0.025 meters, and this multiplied by first the pressure divided with the gas constant and the temperature, and then the logarithmic term that depends on the difference in concentration. Our handbook gives us diffusivity as 1.01 times 10 to the power minus 5 square meter per second. No exact info on pressure is given. Let us assume 1 atmosphere, so 101.325 kilopascal. Well ventilated means no acetone in surrounding air. Partial pressure of acetone infinitely near surface is given by Antoine's equation. Please note that you must use the Antoine parameters for the correct temperature range. We get a partial pressure of 24,728 Pascal, and thus a molar fraction of 0.244. When we put this into Stefan's equation, we get Na equals 1.01 times 10 to the power minus 5 divided with 0.025 times 101,325 divided with 8.314 and divided with 293. And this times the natural logarithm of 1 minus 0.244 divided with 1 minus 0. And we get minus 4.7 times 10 to the power minus 3 mole per square meter and second. So the mass transport out of the test tube is thus 4.7 millimole per square meter and second. However, the evaporation rate is also dependent on the area, with the area as pi times d squared divided by 4 equals 3.14 times 0.02 to the power of 2 divided with 4. We get 3.14 times 10 to the power of minus 4 square meters. Multiplying Na with the area, we get 1.5 micromole per second, which is our answer on question A. In question B, we want to know how the evaporation rate changes over time. In the equations above, everything will be constant except Na and the film thickness. As the liquid evaporates, the film thickness increases, but as the film thickness increases, the evaporation rate decreases. Thus, up to the point where we no longer have enough liquid to keep the liquid area constant, we have an evaporation rate that follows approximately a 1 divided with T shape. One student blew my mind on this exam and went beyond this explanation and showed that, to be more exact, the evaporation rate decreases as 1 divided by the square root of T. But that is way beyond what I demanded for full points on this task.